Welcome to the Deep Dive. Today we're looking at a really interesting paper trying to solve a big challenge in understanding videos.
Right. It's about how we see dynamic scenes where things are moving.
Exactly. We're talking about reconstructing them in 3D and tracking points over time. Usually those are kind of handled separately.
Yeah, that's the standard way. But this paper, St4RTrack, Simultaneous 4D Reconstruction and Tracking in the World, tries to bring them together. It proposes a unified feed-forward framework.
Okay, so for folks maybe just tuning in for the highlights, what's the quick version? What's the core breakthrough here?
Sure. So the key idea really is St4RTrack takes two images from a video, right, different times. And in one shot, it predicts two things. Two 3D point clouds.
They're clouds, okay.
Yeah, and crucially, they're both in the same world coordinate system and represent the scene at the same moment in time.
The same moment. How does that work with two different images?
Okay, so one cloud reconstructs the second image, like its 3D shape, but from the viewpoint of the first image. That gives you the geometry. The other cloud tracks how the points you could see in the first image have moved or changed by the time the second image was taken. So it's capturing the motion.
Ah, I see. Reconstruction and tracking predicted together.
Exactly. And doing it simultaneously like this gives you things like long-range point correspondences and true tracking in a stable world frame, not just relative to the camera.
And the training. That sounded clever too.
Yeah, that's maybe the other big piece. They use something called reprojection loss. It basically lets them train the system using normal, in the wild videos without needing perfect 4D ground truth data, which is super hard to get.
Okay, that's a great summary. Let's dig into the details then. The paper kicks off referencing Taikyo Kanate.
Yeah, the classic correspondence equation.
Right. It really hammers home how vital it is to know which point in one image matches which point in another, especially if you're trying to build a 3D model from different views.
It's fundamental. And for static scenes, there's this beautiful interplay, right? If you know the 3D geometry, you know where points should appear in 2D images. That gives you correspondences.
And vice versa. If you have good 2D correspondences between views, you can triangulate back to find the 3D point locations.
Exactly. It's a really neat self-reinforcing loop in the static world.
But the paper argues this neat loop kind of breaks down when things start moving.
That's their observation, yeah. When you have dynamic scenes, objects moving, maybe the camera moving too, the tendency in the field has been to treat the 3D reconstruction part, figuring out the changing shape, and the 3D point tracking part, following specific points through the motion as, well, separate tasks.
Which St4RTrack argues is maybe not the best way.
Precisely. They're saying, hold on, that synergy between geometry and correspondence isn't actually lost. We just need a way to account for the scene's evolution over time.
And their solution for that is?
Dense 3D point tracking. Basically, if you can figure out the 3D motion, how every visible point is moving and deforming, you're explicitly handling the dynamic aspect.
Right. So the idea is track the motion accurately. And once you've accounted for that motion, the problem almost becomes like the static case again. You can leverage that reconstruction correspondence link.
That's the core argument. You're essentially peeling away the motion layer to get back to that fundamental relationship.
Okay, makes sense. So that brings us to St4RTrack itself. You said the keyword is simultaneous?
Absolutely. It's not a pipeline reconstruct then track or track then reconstruct. It's designed to do both at the same time.
And crucially, in a single, consistent world coordinate frame.
Yes.
Now, for our audience researchers, engineers, why is operating in a world frame so important? What's the big advantage there?
Well, think about it. World frame tracking lets you separate the scene's motion from the camera's motion.
Decoupling them.
Exactly. Imagine a self-driving car navigating a busy street or a drone tracking wildlife. Both the camera and the things it's looking at are moving.
Right.
Understanding the absolute motion of objects in a fixed world frame gives you a much clearer picture of what's really happening dynamically compared to just seeing how things move relative to the camera.
That makes sense. And St4RTrack predicts this directly. No extra alignment step needed.
That's what they claim, yeah. Direct prediction of both reconstruction and tracks in that world frame. It simplifies things, potentially makes it more robust.
So how did they manage this? They adapted existing static methods.
Yeah, they built upon a static 3D reconstruction method called DUST3R. The key was rethinking what the output point maps actually mean.
Okay, so they take DUST3R's ideas, but change the definition of the output for dynamic scenes. Let's break that down. When St4RTrack gets two frames, AI and I, what does it output?
Okay, here's the core trick. It predicts two point maps. And the crucial part is, both are defined at the same time instant, time j, the time of the second image, and in the same coordinate system, the system of the first image.
Wait, both at time j and in frame I as coordinates, even though one input is frame I at time I.
Exactly. It's a specific choice that makes the whole thing work.
Okay, so 2 point maps, same time, same coordinate frame. What does each one represent?
So the network has 2 branches. The reconstruction branch looks at the second image, ij, and reconstructs its 3D content, but expressed in the coordinate system of the first image too. Think of it as asking, what did the world look like at time j, described from position I?
All right, that's the reconstruction part. What about the second branch, the tracking branch?
The tracking branch does something related but different. It looks at the first image too and predicts its content, but as it exists at time j, still in the coordinate system of I.
So it's predicting how the stuff from frame I moved to get to its position at time j.
Precisely. It's directly predicting the 3D motion and deformation of the scene content between time I and time nay.
And they mentioned a DUS23R-like dual cross attention in that tracking branch. How does that help?
That mechanism lets the tracking branch talk to the reconstruction branch during the prediction process. It uses the geometric information being figured out by the reconstruction branch to help decide how points should move.
So the tracking is informed by the shape being reconstructed.
Kind of, yeah. It helps constrain the motion prediction based on the structure at the later time.
Okay, so this redefinition of the outputs seems, well, relatively simple conceptually, but it neatly unifies dynamic reconstruction and world frame tracking.
It's quite elegant, I think, and the next really impressive part is how they train it.
Right, the training without needing full 4D supervision. That sounds crucial for practical use. How do they pull that off?
The key is that the network is designed to estimate everything together. Camera poses, 3D geometry, and the motion. So from the output of the reconstruction branch, that 3D structure of frame j and frame i's coordinates, they can actually work backwards and estimate the camera parameters for frame j. They use a differentiable PMP algorithm.
Differentiable, so they can backpropagate through the camera estimation.
Exactly, that's critical. Once they have an estimate for camera j's pose and intrinsics,
And what?
then they can take the 3D points predicted by the tracking branch, the points from frame I move to time j, and project them mathematically into the 2D image plane of frame j using that estimated camera pose.
Okay. So they predict 3D motion, estimate the camera, and project the moved points into the second image.
Right, and now they can create a loss function, the reprojection loss. They compare these projected points to things they can get easily, like 2D point tracks from an off-the-shelf tracker, or depth estimates from a monocular depth network.
So they're using cheap 2D supervision and single image depth as a proxy for the full 3D motion and geometry. That's clever.
Very clever. It bypasses the need for that expensive, hard-to-get 4D ground truth. And using these off-the-shelf methods for supervision also makes test time adaptation possible.
Test time adaptation. So adapting the model to new videos it hasn't seen.
Exactly. Real videos can look very different from synthetic training data. This adaptation process lets St4RTrack fine-tune itself on a specific new video, improving accuracy.
The paper also introduces a new benchmark, World Track. Why did they need a new one?
Well, most existing 3D tracking benchmarks evaluate performance relative to the camera's coordinate frame.
Right, but St4RTrack works in the world frame.
Precisely. So to properly measure how well methods perform in this more absolute world coordinate system, they created WorldTrack. It evaluates both the 3D tracking and the 3D reconstruction accuracy in that global frame.
Makes sense. And how did St4RTrack do on their own benchmark?
It performed very well. State-of-the-art results compared to strong baselines, including combinations of separate tracking and reconstruction methods.
And the test time adaptation helped there too.
Yes, they showed that test time adaptation provided a further boost, especially improving the results.
Okay, let's maybe position St4RTrack relative to other work. They contrast it with SFM and SLAM.
Right. SFM structure for motion and SLAM are mostly for static scenes or building maps incrementally. St4RTrack is focused on capturing the dense dynamics within a scene over time.
And other learning methods like DUST3R or MONST3R.
Yeah, they mention video depth estimators like RCVD, Casual SAM, etc., and point out they usually don't explicitly model the 3D motion. DST3R is static. MonST3R does handle dynamic scenes.
But the key difference is?
MonST3R reconstructs each frame's geometry independently at its own timestamp. It doesn't explicitly figure out how points move from one frame to the next in 3D, or establish those temporal correspondences like St4RTrack does. Figure 2 in the paper shows this distinction quite well.
What about standard tracking methods? Optical flow, learned trackers?
Those are often great for 2D motion or lifting 2D tracks to 3D, but they can struggle with very large motions, or they operate in the camera frame, not the world frame. St4RTrack aims for longer range world frame 3D tracking.
And things like non-rigid SFM or neural rendering.
Some of those joint methods exist, yeah. But the paper argues some neural rendering techniques focus more on making pretty new views than on accurate motion estimation. Others might need slow per video optimization. St4RTrack is feed forward.
They also mentioned Stereo 4D as concurrent work.
Yeah, Stereo 4D is focused on building a large real-world dataset using stereo videos for supervised training of 4D tracking. St4RTrack is monocular, feed-forward, and uses that self-supervised adaptation, which is a different philosophy.
Let's quickly revisit their notation, ISIJ and IXJJ. Can you unpack that AXBT idea again?
Sure. AXBT means the 3D points X corresponding to the content seen in frame B, represented at time T, and expressed in the coordinate system of frame A.
Okay.
So IXJJ is points from frame I at time J in frame I's coordinates. That's the tracking output, how frame I's content moved.
Yeah.
And IXJJ is points from frame J at time J in frame I's coordinates. That's the reconstruction output, the shape of frame J, but mapped to the reference frame.
And always using frame 1 as the reference A gives them the world frame tracking 1x1, 1x12, and reconstruction 1x1, 1x22.
Exactly. It provides that consistent global reference. And they show how this generalizes DUS-T3R, where time I equals time J for static scenes, and relates to MonST3R, which gives IAI and IXJJ lacking the motion link. For simplicity, they often just write SHJ for the tracking output IJJ.
Okay, let's touch on the architecture quickly. VIT's encoders, Siamese transformer decoder, sounds fairly standard for this kind of task.
The building blocks are familiar, yes. VIT's extract features, the Siamese decoder processes the pair. The key is the cross-attention mechanism that allows continuous information flow between the representations for the two frames, or rather the two output branches, tracking and reconstruction.
Right, enabling that joint prediction.
Yeah, ensuring the two predicted point maps, X1J tracking and XJJ reconstruction, are spatially aligned in that world coordinate system.
And they can initialize training using weights from DUST3R or MAST3R.
Yes, transfer learning. They use MAS3R weights, a DUST3R variant for 2D correspondence, and then pre-train St4RTrack on synthetic 4D datasets like Point Odyssey and Dynamic Replica using ground truth geometry and motion from those datasets.
Okay, now back to that crucial adaptation part. Adapting to real videos without 4D labels. You mentioned the differentiable camera solving.
Right. Using PNP on the reconstruction output gives them the camera pose for frame J, differentiably.
Which allows the reprojection loss. Can you recap the 3 parts of that loss?
Sure. First, LTREG, the trajectory consistency. Project the 3D tracks X1J into 2D and frame J and match them against 2D tracks from something like CoChecker. Scale invariant.
Okay, matching 2D tracks. Second,
L depth, geometric consistency. Take the reconstruction, XJJ, put it in frame J's camera view, get depth, and match that against monocular depth predictions from something like Moj. Also, scale invariant using optimal scaling.
matching depth. And third,
Line, 3D self-consistency. This directly encourages the tracking output, X1J, and the reconstruction output, XJJ, to align geometrically in 3D space for points visible in both views, using CodeTracker again to find correspondences.
got it. Trajectory, depth, and self-alignment consistency. And this loss drives the test time adaptation.
Exactly. They show 2 ways. Instance level, where you fine-tune on one specific new video, freezing the reconstruction branch weight.
To adapt to that specific video's quirks.
Right. And domain level, where you adapt on a few samples from a new domain, and then that adapted model can be used directly on other videos from that domain without more tweaking.
Okay, let's talk results. On their World Track benchmark for world coordinate tracking, how did it stack up?
Very well. State-of-the-art APD 3D scores on datasets like ADT, Panoptic Studio, Point Odyssey, Dynamic Replica. Test time adaptation gave a noticeable boost, especially for dynamic points. It even did well on Panoptic Studio, where the camera is static, beating camera frame method sometimes. And it generalized okay to longer sequences than it was trained on. EPE metrics confirmed the good performance.
And for dynamic 3D reconstruction, on data sets like Point Odyssey and TM dynamics.
Also, state-of-the-art APD and EPE after scale alignment. It beat MONST3R and BSD3R. Interestingly, MONST3R didn't do as well even with alignments, suggesting the joint tracking really helps the reconstruction quality. Test time adaptation didn't change reconstruction much because they freeze that part during adaptation.
They also showed qualitative results, Figure 4.
Yeah, nice visualizations showing the 3D point tracks and the 3D reconstructed clouds together in the world frame. They look well aligned and consistent over time, which is good visual confirmation.
And the Ablation Study, what did that confirm?
It showed pre-training is really important. Without it, the outputs weren't aligned. It also clearly showed test time adaptation fixing errors like drifting points near moving objects. And the quantitative ablation in the supplement showed that removing any part of the reprojection loss, trajectory, depth, or alignment hurt performance.
Makes sense. Now, they did mention some limitations.
Yeah, working frame by frame can cause issues with scale drift over longer sequences or problems with very large camera moves or heavy occlusions.
Things that maybe looking at more frames at once could help with.
Potentially, yeah. They suggest incorporating temporal attention across multiple frames as future work, maybe getting richer motion information that way.
They also noted the synthetic training data isn't perfect.
Right. Limited realism and diversity means test time adaptation is often needed, and it might still struggle with really complex, unusual real-world motions not seen in training.
So future directions are mostly about scale.
Pretty much. Bigger, better, more diverse training data and large-scale pre-training when compute allows. They think that's the path to making it handle even tougher real-world videos robustly.
Okay, so wrapping up, St4RTrack really does seem like a significant step. A feed-forward way to get simultaneous 3D tracking and dynamic reconstruction all in world coordinates from just monocular video.
Absolutely, and providing the World Track benchmark is a contribution in itself for evaluating the specific capability. The results look strong, and that test time adaptation makes it much more practical than relying purely on supervised learning with hard-to-get 4D data.
It definitely prompts you to think, doesn't it?
Yeah.
How could this unified understanding of dynamic 3D seeds, detached from camera motion, impact fields like robotics or AVs or maybe AR/VR, content creation, anywhere that deep understanding of real-world dynamics is key?
Yeah, decoupling that scene motion is powerful. It opens up possibilities.
A lot to consider there. Well, thanks for breaking down St4RTrack with me today.
My pleasure. It's fascinating work.